So we're going to talk about what determinant means in terms of volume. So to make that precise, we actually need to define volume. So to define the volume of a set omega in Rn, what we'll do is we define the volume of a simple set so we'll use boxes, so rectangular parallelepipeds with sides parallel to the coordinate axes. And then we'll define the volume of a general set omega by sort of shrink wrapping it. With boxes. Okay, so let's define first off a box and the volume of a box. So a box B in Rn is a set of the form, so it's going to be all n tuples of numbers where yj is between xj and xj plus rj. Okay, and so this is the same thing as the Cartesian product of the intervals x1 plus r1 crossed with up to xn plus rn. So so this is a Cartesian product of closed intervals. The book does it in terms of open intervals. I find it a little more convenient to use closed. It doesn't really make a big difference. And I guess it's worth pointing out here that these RJs here, these are the side lengths of the box that we're interested in. Okay, so then we can define the volume of a box B. So this is denoted by vol B, and it's just R1 times up through Rn. So in other words, we're taking the product k equals 1 through n of Rk. So it's the product of the sides of the lengths of the sides of the box, just like you'd expect. So now we will need one other idea to extend this to our general set. So for omega, our general set in Rn, we say a cover of omega is a collection of boxes whose union contains omega. Okay, so Then we can define the volume of omega as the infimum, or lower limit, over all covers, and then where we sum up the volume of the boxes in that cover. So with a little bit more detail, this is the infimum over the sums of the volumes of the BJs. And yeah, so let's say, so this is J equals 1 through M. And then this is where such that omega is contained in the union of these things. Okay, so just to make this a little bit more visual, suppose we have some set omega. So here's a picture of omega in Rn. And then let's cut it up into little boxes here. So we've got B1, B2, B3, B4, B5, B6. And so here we've got like the sum of the volumes of boxes 1 through 6 is going to be everything that's inside that. Here, let me get a highlighter here. Okay, so that sum is going to give me the measure of everything that's in this region here. And you can tell that this is sort of a sloppy approximation. I wasn't especially careful. I got a lot more than I wanted to from the exterior of omega, right? So I might do something a little bit more accurate. So maybe I'll take this one instead. And so now here's another one. And now I've got B1, B2, B3, B4, B5, B6, 7, 8, 9, 10, 11. So I had 11 B's in that one. Okay, so over here, the measurement I get is J equals 1 to 11 volume of the BJs. So here's my cover number 2, and here's my cover number 1. And you can tell with cover 2 here, the green region that I'm getting, it's much more accurate. It's much closer to the actual measurement of omega. I've overshot very little because I'm choosing my boxes a little bit more little bit more accurately. And then I can consider the collection of all possible covers of omega, and I take the infimum. So the it's potentially going to be decreasing, so that one is definitely a bigger estimate than this one, and we go toward the infimum getting ever smaller, and then that takes us to the volume of omega. So that's the definition for the volume of omega by shrink wrapping it with covers by boxes.